Welcome to the 20-second lecture video for Physics 4A. In this optional lecture set, we cover additional topics and discussions relating to universal gravity and orbital dynamics that we couldn't cover in our one single lecture for Newton's law of universal gravitation. We have a couple simulation demonstrations, one using PhET simulation, My Solar System. The demonstration here uses the old Flash version. The new HTML5 version on PhET website now may be able to do something similar. And a second simulation demo using a commercial software called SpaceEngine. Both demonstrations illustrate laws and ideas discussed in lecture. We have a demonstration of constraints on orbital parameters from a homework problem back in chapter 11, where not properly accounting for Newton's law of gravity could result in unphysical orbital parameters. More of a problem for physics textbook question writers than physics students. A reading through a section of Feynman Lectures, a highly recommended classic now available for free on the Caltech website, and a couple derivations of special orbits around the Earth, mainly a geosynchronous orbit and a low Earth orbit. By the way, I think I used geosynchronous when I meant geostationary. When these distinctions matter, you should probably look it up and use it correctly. This wraps up everything we will cover, including optional topics relating to gravity. You will see more mathematics relating to inverse square laws like gravity when we cover Coulomb's law in Physics 4b. For this class, next week we start looking at applications of the mechanical principles we have covered, starting with the simple harmonic oscillations. So this is the flash simulation that illustrates orbits. It's kind of fun. I wanted to show you this workaround so that you can run it for yourself and kind of play with it. This is the kind of the typical sun and a planet orbit. I guess you can imagine this is Mercury. It's kind of slightly elliptical. I think this is a little more elliptical than Mercury's orbit. And this illustrates Kepler's first law. And you can get what Kepler's first law says, that planets orbit the sun in elliptical path with the sun at the center of sun at one of the two foci. This is one of the two focuses. There's another focus of ellipse here that there's just nothing there. So it illustrates Kepler's first law. To derive that mathematically is a little bit challenging because you have to be good at vector calculus, and there are some textbooks out there that'll do that derivation. If someone's interested, let me know. I can find the textbook and point you to it. And this is really Newton's greatest, most significant contribution in the whole discussion, I guess, debate or discovery of what kind of law of gravity is, because a lot of people other than Newton have theorized it might be an inverse square law, but I guess only Newton was good enough at calculus to actually work out that Kepler's laws were known. Kepler's from a generation before Newton, so Kepler's laws of orbital motion were known at Newton's time, and Newton could derive Kepler's first law by assuming that gravity is inverse square law of force, and using his the Newton's laws of motion, the force produces acceleration and all that. So you can play with other presets like sun, planet, moon. These are fun. So I'll just leave that for you to play with. What I want to end. Oh, this is a fun one where if you watch it for a bit, you will see something interesting happen. So what they label as a planet, they give it a little bit of, yeah, planets have a mass number 2. It has a little bit of mass. So as it swings near a comet, it'll affect it gravitationally. That's why orbit of the comet kind of keeps changing over time. And this is one of the fun presets that are set in a way that kind of demonstrates how comets can get knocked out of their orbit by close by path of the planet. Here it'll slow it further down and make it swing in. Yeah, that's fun. But what I wanted to get to was kind of the things that you don't see in nature. I mean, you can pick out things where they are kind of similar. So you can imagine um, this closer inner thing is maybe one of the terrestrial planets, Mars. And this might be one of the comets that are on a somewhat elliptical orbit, but not too far out. And this would be another comet that's also in an elliptical orbit that's farther out. And this setup illustrates Kepler's second law of planetary motion, which is that, let me just stop them briefly, that so you can imagine looking at one of them and tracking motion of a single comet over its orbit. You see that when it's farther out, they move at a certain speed that's slower than the speed that they move. Like it zoomed by this portion really fast, and that illustrates Kepler's second law because you can imagine kind of setting this up. So using something like, I don't know, a half a second as your duration of time. So here's the here's the area swept by line connecting the sun and the planet over that half a second. I'm just going to click start and then stop as quickly as I can. That's going to be close to half a second. So that's the area swept out by the line connecting sun and the planet. It's a thin slice of thing, not drawing straight lines very well. And when it's closer, okay, around here, I'm gonna again do the same thing. Click start, and as quickly as I can, click stop. That's gonna be close enough to half a second. You can see that because it's moved farther, um, it, even though this radius is less, when you look at this area, compare that to this area, they should be the same, and that's what Kepler was able to figure out from the record of the orbit of Mars. And after figuring out his first law, he, yeah, so that's Kepler's second law. And the claim that I made in the lecture is that this Kepler second law can be um, it can be derived from conservation of angular momentum. And in this setup, it might not immediately look like angular momentum is conserved because when you see this planet out here, it's moving pretty slow. And when you look at the planet in here, it's moving pretty fast. So how is angular momentum conserved? Well, it's conserved because when you consider these distances are at aphelion and consider the distance are at perihelion, then the angular momentum in terms of the rotational inertia times angular velocity, the rotational inertia, it depends on the distance. So for a point mass like that, rotational inertia is the distance from the center squared times the mass of the thing. So when it's an aphelion, its radius is larger. So this rotational inertia is going to be greater. So that requires this angular velocity to be less in order for angular momentum to be the same when it's at this point and it's at this point. And in fact, that is omega smaller proportionally. Omega is smaller inverse proportional to like inverse square. So that if you are, instead of tracking this in terms of omega, if you are writing this in terms of the tangential velocity divided by r, then one of these r's canceled out by one, and your the tangential speed will be inversely proportional to the distance. So So that's one way of looking at how, in this situation where you see the speed of the orbiting objects change, that's consistent with the angular momentum conservation. But maybe you are puzzled by my assertion that angular momentum is conserved in this setup that clearly has external force. This sun here, it's a body that's external to this planet. It's clearly exerting this force of gravity that's going to be equal to, what's given by Newton's law of universal gravitation. So given this external force, why should the angular momentum be conserved? And this is because gravity is a central force, meaning gravity is in the exact direction that I have drawn. It acts on this body, pointed in the direction towards this center where it's coming from. And when you look at the expression for torque, torque is the displacement vector cross product with the force, or in a kind of less vector like language, you can think of it as the lever arm times force. Here, the displacement vector is the vector from the sun pointing to here. This is my r. So when you take cross product of this vector with this vector, that's going to be 0 because they are at 180 degrees and this cross product will be 0. Or another way to put it is lever arm is the perpendicular component of displacement and perpendicular to the force. And with the force pointed that way, here the perpendicular component is 0. So throughout the entire orbit of this planet, there's no point at which lever arm is not 0. So even though there is an external force on it, there is no external torque on it. That's why the angular momentum should be conserved. So yeah, so the relationship that you have from Kepler's second law, you can connect it directly to angular momentum conservation, and this is the illustration of that. So yeah, this question. So I can do it. Um, Let me do it this way. So let me answer it because this is one of those questions. The answer is actually pretty easy. It's not a hard question. There was just something that I want you to point out, which is more of my personal interest than actually just answering the question. So let me first just answer the question that I can do in like 5 minutes, and then I will show you the question coding to point out some consideration that goes into this. So it says on Earth satellite, it has apogee, that's this point A, at 1600 kilometer above surface of Earth. So I think the way it's giving these numbers, above the surface of Earth, this is really, if we are measuring it from center of the Earth, this is supposed to be the distance above the surface of the Earth plus the radius of Earth. So that is my RA. And Paris at 600 kilometer above. So this would be now 600 plus 6,370. At apogee, it's so this speed is 6.83 kilometers per second. What is its speed at perigee? Okay. And as you're reading the question, so I hope you're thinking of applying conservation law. And as you are, because as I was saying, conservation laws are when they work, they are the simplest to use, and when they don't work, they are also simplest to rule out their usage. So it's one of the first things you should try, because either it'll work or you will find out quickly that it won't work. As you apply conservation law, you have conservation of energy, momentum, and angular momentum. And you can technically use conservation of energy. just a little bit more complicated, so I'll skip that for now. Conservation of momentum is a little bit hard. You can clearly see that momentum is changing between A and P, and I guess if you include the momentum of Earth, maybe it'll work. But so even though momentum is conserved in this setup, it's difficult to use it in a way that will help you answer this. That leaves you with the third, the angular momentum. Is it conserved? And the answer is yes, it's conserved. Because so as this satellite is orbiting, it's only under the force of gravity, and while gravity is an external force to the satellite, gravity force it only acts in a line that connects. It only acts in a line that connects between the satellite and the Earth. It's what's called central force. And with a force like this, angular moment, the torque due to that is always zero because the lever arm is zero. So as this satellite orbits, the torque due to gravity is always zero. So angular momentum will be conserved. So that's what we are going to use. So we can use the expression for angular momentum. That's the lever arm times momentum, or lever arm times mv. And we are going to say angular momentum at point A is equal to angular momentum at point B. This is the statement of conservation of angular momentum. So at point A, we have the apogee distance, RA. And with the apogee and perigee, this distance works out to be the perpendicular distance. All the other points along the orbit, it gets a little complicated, which is why we don't ask. Apogee and perigee, perpendicular, I can just use that as my lever arm, times velocity or speed at apogee is equal to the perigee distance, RP, times m times the speed at perigee. Oh, masses cancel out, which is great because the question didn't give us that. So I can just solve for, oops, that's meant to be p. I can just solve for the speed at perigee. So the expression for speed at perigee is equal to the ratio of the two distances, RA over RP, times the speed at apogee. And so here, because of these ratios and whatnot, I'm gonna just rely on the units to cancel out, and the final answer I want is in kilometers per second, so I'll just plug this directly in. The unit will just work out. So I have the RA, that's 1600 plus 6370, divided by perigee distance, 600 plus 6370, times the speed at apogee, 6.83. So it's pretty simple answer, 7.81. And because the angular momentum is the simplest way to do this question, sometimes question writers forget that the other two conservation laws actually still apply. In particular, conservation of energy still applies. Then you might think, but we already had all the knowns and unknowns to solve this just using conservation momentum. So if we have additional equations that apply, does that mean this is an overdefined system? And yeah, the answer is yes. When you have a system like this, you are not free to simply randomly choose these distances RA and RP. You can't. If you simply randomly choose these distances, you might accidentally come up with a system that's physically impossible. So for this question, you can actually use conservation of energy, and the question has been painstakingly programmed to exactly allow you to do that, because system doesn't randomly generate those distances. I mean, a portion of it gets randomly generated. It randomly generates. Okay. So it randomly generates the distances. What it doesn't randomly do is one of the knowns that you had in the question, the speed at the perigee, there's an actual solution. Once you specify both the perigee and apogee, okay, those numbers you can randomly choose. But after you've done that, the speed at either of those 2 points is already completely determined. You can't simply randomly pick. So the question code does that. So if you try to solve this, if you try to solve this question in just using conservation of energy, you can, and because we have been very careful in coding this question carefully, the solution you get through conservation of energy will actually match this answer, and it'll also be correct. But we recommend that you use conservation of angular momentum because it's conservation of angular momentum because it's a lot easier, and that's the intended solution method for this question. So I have talked about this before. These are, if you read the preface, then he would describe where it comes from. So this came from lower division introductory physics, introductory in the sense that these are the first physics classes that science and engineering majors take at Caltech. And he gave these lectures first 3 semesters, I think. That's what volume 1, 2, 3 divisions are. And guess, does it tell you the year? It was done in the 1960s, yeah. So that's where it comes from, and I think I've said this a couple times that you can't really use this as a textbook for a class because the orders are so unusual. He's talking about conservation of energy long before even introducing kinematics. And so with that caveat, it is a classic. So if you ever major in physics, it's something that many of your physics professors would have read or at least heard about. And from my personal perspective, I think the first summer when I was in college, I spent the first few weeks of the summer just reading through the book and the volume 1. And I remember just getting a really fresh perspective, understanding the laws of physics and the physics problem solving in ways um, that I didn't quite get from the textbook that we were using then. So this is a kind of supplemental thing because it gives that perspective. Now, one thing I do have to say is that it's from the 1960s. So to the extent that there have been progress in physics, fundamental physics, or engineering, that wouldn't be reflected in this book, especially in the fields of engineering. With the fundamental physics, there haven't been any new fundamental paradigm shifting discoveries in physics since about 1980s or so. That's when what we call standard model of particle physics was completed, and then since then there have been particles discovered. There have been discoveries, but none of the discoveries since then changed the paradigm of how we are organizing things. So to that extent, the encouraging thing here is that a lot of this is kind of up to date because it's the sort of thing that doesn't change. So, anyways, so I had a couple of sections picked out that I wanted to just read through. I think this was when I was teaching astronomy. There was story about Newton and his discovery of law of universal gravitation that I remembered from somewhere that I was looking for authoritative reference to cite it properly in my lecture slides, and it's here. So I'll just briefly summarize the first few sections and then read it through the one section where that contains the excerpt that I'm looking for. So in section 7.1, he's talking about planetary motions. He starts out with a summary of what we'll get to in a bit, the Newton's law of universal gravitation. This is the inverse square law statement about the gravitational attraction between everything. Now, there's a story of getting to this law because it's us modern folks. We have the advantage of standing on the shoulders of giants, um, benefiting from all the work that have been done, all the observations that have been made. So we have the luxury of starting from this law if we wanted to. And in this and the next couple sections is where Feynman tells the story of getting to this law. So we start out with the planetary motion. So the first thing that led people to think about what led to the law of gravitation is observing motions of planets among the stars, and trying to come up with a theories that would account for all the features you see in those motions. And he skips through some things. He's skipping through like Galileo and all the stuff. He's beginning with the beginning of modern astronomy, which is the observations of Tycho Brahe, and Kepler is the guy who analyzed Tycho's data, and as he was analyzing it, he was able to derive the he was able to deduce the following laws. These are what we might call a phenomenological law, in that he his starting point was data. So Kepler's first law, we covered this by the way. Kepler's first law says that planetary motions take an elliptical path. And how did he know that? Well, he looked at this data. He first analyzed it under the assumption that it might be a circle, and turned out it didn't really fit if it was a circle. So he started thinking of other shapes so that might be similar to circle but still fits, and what the shape that worked out turned out to be ellipse. And Kepler's second law deals with how the speed of the planets vary as they go around in this ellipse. This is the picture that demonstrates it. And the third law, I think there was about a gap of 10 years between his first two laws and the third law. It deals with comparing different planets. He found out the planets that are farther away from the sun move slower. Now, um, so we have these Kepler's three laws of planetary motion, and I call this beginning of modern astronomy because these laws are still today true, with the caveat that it's true to the extent that the sun is the only source of gravity in the solar system, which is, to a largely good approximation. So under that approximation, Kepler's laws are still true. It's not like the Copernican heliocentric model with the perfect circles that we had to get rid of. Kepler's laws are still true with a very specific bit of approximation. Um, but as a law of physics, what it lacks is it's describing a very particular category of object, and um, and physics being fundamental science, we think there's a fundamental law that describes everything. And having a law of planetary motion that somehow doesn't apply to terrestrial objects, that's um, that's not satisfactory. So this is where he takes a little bit of break in 7.3 to talk about Galileo, well, not Galileo, talk about Newton, well, Galileo and Newton. I think the way it's usually taught, at least I teach it out of chronological sequence. So Kepler was a contemporary of Galileo. In fact, when Galileo, there's a letter that Kepler wrote to Galileo as Galileo was writing and advocating for heliocentrism. Tycho Brahe is actually he's not contemporary of Galileo. He comes before Galileo, and so we talk about Galileo more when we talk about like inertia, principle of relativity, and that stuff. Yeah, and then Newton, it comes later after Galileo, after Kepler, and Newton's laws of motion are what we spent quite a bit of time um, working through this semester, and this is what he describes. And this is the section that I want to read in more detail. So as we get into this section, what we should have understanding of is the discoveries of Tycho Brahe and Kepler, their um, their their description of how the planets move, and development of some basic mechanics, Newton's three laws of motion, describing force, mass, and acceleration. So, so this is the culmination of all that understanding and knowledge. So, section 7.4. From his better understanding of the theory of motion, Newton appreciated that the sun could be the seat of organizational forces that govern the motion of the planet. Newton proved himself, and perhaps we shall be able to prove it soon. And by the way, it's quite um, you have to be really good at calculus to be able to prove this. That the very fact that equal areas are swept out in equal times is a precise signpost of the proposition that all deviations are precisely radial. That the law of areas is a direct consequence of the idea that all of the forces are directed exactly toward the sun. Oh wait, so that is actually something that relates to the angular momentum and torque. So maybe that you don't have to be so good at calculus to prove that. Keep going. Next, by analyzing Kepler's third law, it is possible to show that the farther away the planet, the weaker the forces. If two planets at different distances from the sun are compared, the analysis shows that the forces are inversely proportional to the squares of the respective distances. With the combination of the two laws, Newton concluded that there must be a force inversely as the square of the distance, inverse square, directed in a line between the two objects. Being a man of considerable feeling for generalities, Newton supposed, of course, that this relationship applied more generally than just to the sun holding the planet. It was already known, for example, that the planet Jupiter had moons going around it as the moon of Earth goes around the Earth, and Newton felt certain that each planet held its moons with a force. He already knew of the force holding us on the Earth, so he proposed that this was a universal force, that everything pulls everything else. This discovery, by the way, was um, by Galileo, and it was one of the discoveries that supported the heliocentric idea, heliocentric model, and refuted some of the objections to the heliocentric model. The next problem was whether the pull of the Earth on its people was the same as its pull on the moon, i.e., it has, that is, inversely as the square of the distance. If an object on the surface of the Earth falls 16 feet in the first second after it is released from rest, how far does the moon fall in the same time? We might say that the moon does not fall at all, but if there were no force on the moon, it would go off in a straight line, whereas it goes in a circle instead. So it really falls in from where it would have been if there were no force at all. We can calculate from the radius of the moon's orbit, which is about 240,000 miles, and how long it takes to go around the Earth, approximately 29 days, how far the moon moves in its orbit in 1 second, and can then calculate how far it falls in 1 second. So this is a footnote describing what falling means. How far the circle of, so if you imagine a straight line path and compare that with a circle, there's a distance there. That's the distance that's being described as falling. This distance turns out to be roughly 1/20th of an inch in a second. That fits very well with the inverse square law because the Earth's radius is 4,000 miles, and if something which is 4,000 miles from the center of the Earth falls 16 feet in a second, something 240,000 miles or 60 times as far away should fall only one 3,600th of 16 feet, which also is roughly 1/20th of an inch. Wishing to put this theory of gravitation to a test by similar calculations, Newton made these calculations very carefully and found the discrepancy so large that he regarded the theory as contradicted by facts and did not publish his results. 6 years later, a new measurement of the size of the Earth showed that the astronomers had been using an incorrect distance to the moon. When Newton heard of this, he made a calculation again with the corrected figures and obtained a beautiful agreement. The idea that the moon falls is somewhat confusing because, as you see, it does not come any closer. The idea is sufficiently interesting to merit further explanation. The moon falls in the sense that it falls away from the straight line that it would pursue if there were no forces. Let us take an example on the surface of the Earth. An example released near the Earth's surface will fall 16 feet in the first second. Oh, yeah. So it's this. Let me try doing this. Open image in new tab. Yeah, and let me try having this on the side so that we can read and both see the description of the. Yeah. So in this coming section, he's describing this apparatus. I refer the moon falls in a sense. Okay. An object released near the Earth's surface will fall 16 feet in the first second. An object shot out horizontally will also fall 16 feet. Even though it is moving horizontally, it still falls the same 16 feet in the same time. Figure 7-3 here shows an apparatus that which demonstrates this. On the horizontal track is a ball which is going to be driven for the little distance away. At the same height is a ball which is going to fall vertically. And there's an electrical switch arranged so that at the moment the first ball leaves the track, the second ball is released. That they come to the same depth at the same time is witnessed by the fact that they collide in midair, collide here. An object like a bullet shot horizontally might go a long way in 1 second, perhaps 2,000 feet, but it'll still fall 16 feet if it is aimed horizontally. What happens if we shoot a bullet faster and faster? Do not forget that the Earth's surface is curved. If we shoot it fast enough, then when it falls 16 feet, it may be at just the same height above the ground as it was before. How can that be? It still falls, but the Earth curves away, so it falls around the Earth. The question is, how far does it have to go in 1 second so that the Earth is 16 feet below the horizon? In figure 7-4, I think that's another figure, yeah. We see the Earth with its 4,000 mile radius and the tangential straight line path that the bullet would take if there were no force. Now, if we use one of those wonderful theorems in geometry, which says that our tangent is the mean proportional between the two parts of the diameter cut by an equal chord, we see that the horizontal distance traveled is the mean proportional. I think he means a geometric mean. I think. And by the way, this theorem in geometry, I myself don't remember that geometric theorems are often very useful, and it takes a lot of effort to learn really thoroughly. So I would encourage you to try to make sense of this. Maybe go back and look up your geometry books if this theorem was proven. If not, look it up, see where you can find the proof of it. So what I'm saying here is that we see the between mean proportional between the 16 feet fallen and the 8,000 mile diameter of the Earth. the square root of this quantity, which is how you calculate geometric mean, it comes out very close to 5 miles. If the bullet moves at 5 miles a second, it then will continue to fall toward the Earth at the same rate of 16 feet each second, but will never get any closer because the Earth keeps curving away from it. Thus, it was that Mr. Gagarin, Yuri Gagarin, the Russian cosmonaut, was the first person to be on the to achieve orbit. Maintained himself in space while going 25,000 miles around the Earth at approximately 5 miles per second. It took a little longer because he was a little higher. Yeah. S is the distance followed in 1 second. Mm, yeah, I guess that's the ambiguity. So yeah, falling, if you measure it relative to your original orientation, should be perpendicular this way. If you measure relative to where you are, then it should be drawn this way. But so this is the beauty of calculus. This drawing, which would be inaccurate when you're dealing with large distances. When you're dealing with very small distances, it becomes approximately correct. So, yeah, and and this is all great. And this paragraph is here is where Feynman uh, uh, demonstrates how we judge scientific theories. So let me continue reading. I'm gonna go back to my original view. So any great discovery of a new law is useful only if we can take more out than we put in. Now, Newton used the second and third of Kepler's laws to deduce his law of gravitation. What did he predict? First, his analysis of the moon's motion was a prediction because it connected the falling of objects on the Earth's surface with that of the moon. Second, the question is the orbit an ellipse? We shall see in a later chapter how it is possible to calculate the motion exactly. And this is actually the part where you have to be good at calculus. And indeed, one can prove that it should be an ellipse. So no extra fact is needed to explain Kepler's first law. Thus, Newton made his first powerful prediction, reduced 3 laws of planetary motion down to 2, more or less. The law of gravitation. Wait, what is? Oh, the professor not giving. There are textbooks, lower division physics textbooks that do go through this. And again, I'll say you have to be really good at calculus to do it. I myself wouldn't try to do it without prior preparation because again, you have to be really good in calculus. And I'm not all that good enough in calculus to do it without prior preparation. Okay, the law of gravitation explains many phenomena not previously understood. For example, the pull of the moon on the Earth caused the tides, hitherto mysterious. The moon pulls the water up under it and makes the tides. People had thought of that before, but they were not as clever as Newton, and so they thought there ought to be only one tide during the day. The reasoning was that the moon pulls the water up under it, making a high tide and a low tide. And since the Earth spins underneath, that makes the tide at one station go up and down every 24 hours. Actually, the tide goes up and down in 12 hours. Another school of thought claimed that the high tide should be on the other side of the Earth because, so they argued, the moon pulls the Earth away from the water. Both of these theories are wrong. It actually works like this. The pull of the moon for the Earth and for the water is balanced at the center. But the water which is closer to the moon is pulled more than the average, and the water which is farther away is pulled less than the average. Furthermore, the water can flow while the more rigid Earth cannot. The true picture is the combination of these two things. What do we mean by balance? What balances? If the moon pulls the whole Earth toward it, why doesn't the Earth fall right up to the moon, collide with it? Because the Earth does the same trick as the Moon. It goes in a circle around the point, which is inside the Earth but not at its center. The Moon does not just go around the Earth. The Earth and the Moon both go around the central position, each falling toward this common position as shown in this figure. This is the common point, very center or center of mass or center of weight of Earth and Moon. Um, the motion around the common center is what balances the fall of each. So the Earth is not going in a straight line either. It travels in a circle or ellipse, which is quite close to circle. The water on the far side is unbalanced because the moon's attraction there is weaker than it is at the center of the Earth, where it just balances the centrifugal force. The result of this imbalance is that the water rises up away from the center of the Earth. On the near side, the attraction from the moon is stronger, and the imbalance is in the opposite direction in space, but again, away from the center of the Earth. The net result is that we get two tidal bulges. So, yeah, I think this is the section I want you to read through in detail, mostly for this description here of Newton's discovery and testing of the inverse square law of gravitation. The, this is a description of science as it ought to be. You know, we make a prediction and we test that prediction against experiment, against known facts, experiment data. I guess Newton didn't really do any experiment of his own. He was relying on measurements made by others. And, you know, when they disagree, then we we fix it, or we maybe we learn from that disagreement. So here, I guess what Newton learned was, well, he found the discrepancy and he thought the theory wasn't correct because, you know, it was contradicted by existing fact. But, you know, he didn't just forget about it, get rid of it entirely. And when he learned of an update that might change the prediction, he redid the calculation, and once we had agreement, then he published and all that. That's a kind of an example of how science ought to work. We make predictions and we test it, and you know what to do when the predictions don't agree with the experimental results don't agree with the prediction. That's a whole topic on its own. I think there are scientists who think, especially in other fields, who think that we call it publication bias in the sense that we scientists tend to want to, and the peer-reviewed journals tend to want to publish only the results that show positive result. Kind of equivalent to Newton not publishing his result because he saw a discrepancy that he considered to be too large. And what if no one never ever made a new measurement of distance to the moon within Newton's lifetime? Then what would happen? So there's in the scientific world, there's a bias for publishing and making others aware of the positive result, as in results that seem to show something new. When someone did an investigation and it's a negative result, as in the result didn't show anything apart from what someone would just guess offhand, then because it's not considered novel, people don't publish it, and you know there's a reason for that. But sometimes that kind of publication bias can lead to systematic bias in a field that's not healthy for the field. So that's a whole another topic, but I'll leave that for you. But I guess what I can ask, if you're interested in the topic, what you can do for yourself is search up something called the replication crisis, because it has to do with crisis to a degree of where there are some scientific results that don't seem appear to be replicable. It's not something that affects physics all that much, but it's a it affects how we. It's an epistemological. It's a problem of knowledge gathering because we rely on this scientific process, and there seem to be results that we thought were reliable, but are not apparently. So I'll leave that there. It's not really a physics topic. So I was thinking through what I could do today, and I think this is something that I've done for my astronomy class, but I think it might be worthwhile to do here. So this is it's just a link to a website for the software. It's technically a game. There is a free version that's I think available here. I'm going to use the one that I bought on Steam. It's a well, I guess they're calling it Universe Simulator. It's a really a good software for illustrating some of the things in astronomy. You do have to be careful to, especially when you're using for real world demonstration. You have to turn off what's called a procedural object. But so I just want you to just to play with it and kind of talk over some things. So yeah. So let me do that. I'm Let me do it this way. So let me run the space engine, and I think I have to change my share setting. I have this vague recollection of doing the normal Zoom share setting with the SpaceEngine before, and doesn't quite come through right. So my experience running this software in previous classes was with the Zoom's regular share setting. I think this comes it's trying to send it through too high resolution. So I'm going to just change my share settings so that it's optimized for video clip. I'll see how well that goes. Um, so this is a quite demanding software. It actually um, it uses a fair amount of computing power, both in terms of the CPU and GPU. And I have a laptop that I got this past May that's more powerful than any of the computers I've had before. Then running this software wouldn't really have been possible and have a smooth-ish Zoom experience. So, anyways, so I changed the settings. Hopefully, it'll turn out a little bit better. So this is planetarium software. Let me just do a couple of things here. I'm gonna turn off the orbit because that's it's useful for some things, but I'll do that later. Let me see here. Let me go to the more familiar view first, planet Earth, and and as I was saying, it's technically a game. You can I guess it's a kind of odd kind of game, even odder than Minecraft, because even in Minecraft you can, affect the world you are in. This is a more of spectator kind of game, so you can look at the things. Let's see, are we on real time now? No, that's not real time. Let me try to change to yeah. So this is real time. This is right now, today, and let me see. I feel like I'm upside down on this. Let me just because that's South Pole and that's on the top side here. So there's some a bit of control that I want explain over explain. So I'm using mouse for control, and depending on whether I'm clicking the left button or right button, the how the camera view changes shifts, and there's a whole shortcut of things that I try to remember. If I forget and I need to look it up, I'll come back here and look it up. Um, so what I want to start out with, can I just close this? With this, so that object there, it used to be called, I think, Andromeda Nebula, because looks like a nebulous kind of lens-shaped thing. It so it stands out by its size because it doesn't look like a point of light, and it's not the sun, it's not the moon. It's in terms of angular size, it's bigger than the planet. And let me zoom in like zooming in with a telescope. So when you um, as the people were actually observing Andromeda Galaxy, what we now know as Andromeda Galaxy with the telescope, they saw these features. And I think it's a accurate distance measurement to Andromeda Galaxy that established it as being something that must be outside of Milky Way galaxy, our own galaxy. That's relatively recent. I think that happened somewhere in the 20th century, early 20th century. So, well, this is a view of Andromeda Galaxy. Now, so all of this is an interesting thing to look at in an astronomy class, and I do now in a physics class. I guess other than just appreciation for the natural world, or the Phys, the natural world we live in. It might not um, look like a terribly relevant to physics. So let me show something that has a more direct connection to what we've been covering. So one of the things I was thinking through, and that's why I thought demonstration of this software would be good, is the discussion of the gravitational interaction with the celestial bodies. um, there was a in the section of the Feynman lectures that I was reading through on Monday. There's the one that talks about Earth falling towards the moon or something along that line, and you can see those orbital mechanics in this software. So I'm going to turn on the orbits of the things because that helps me one orient myself and look for the features of the things that I think would be interesting. Let me make sure I'm on the correct side of the hemisphere. Just for consistency's sake, I want to be, yeah, okay, I want to turn this around. Because most of the orbital pictures that shown will normally place you so that north is up. That's what I'm trying to do. So that's south, that's the Antarctica, so that's down. And this is the north, which is up. Okay, good. So so you see several lines drawn here. Let me zoom out or move away from the Earth so that I can show some of these better. So right now I have Earth selected, and Earth is going in kind of two different kind of orbit. So there's a larger orbit of Earth around the Sun, and that orbit is represented by this line here. So to show that, I had to zoom way out. When I zoom way out with the sun in view, you can see this is the orbit of the Earth and Moon system around the sun. Let me go back to. So what these orbits are describing is orbit of the Earth-Moon system around each other. So that's moon. When I click it instead of moon, it'll actually select one of the Apollo spacecraft that's landed on the moon. Let me use the search feature to select the moon. So that's the moon. It looks like it's orbiting Earth, and that's the description we can give of Earth as being, moon as being gravitationally bound to Earth. And this orbital motion of moon is moon falling towards Earth, in that if there was no gravity of Earth, it would be going in a straight line. So compared to that straight line, it's falling away from that straight line into this circular-ish orbit. Now, I said I would demonstrate what Feynman was talking about, Earth falling towards the moon. So when you look here, Earth is not stationary in the kind of Earth-Moon system. Earth itself is actually also orbiting. It's orbiting in this small circle here, and the kind of the central point that Earth is orbiting around, and Moon is orbiting around actually as well, is this point here. This is what the program is calling planetary barycenter, or center of mass. This point is the center of mass of Earth and Moon. So Earth is, massive enough that this center of mass of the Earth-Moon system, it lies inside the Earth. You can see as I change my observation point around, it's just inside the Earth. But Moon is also heavy enough. Moon is actually quite unusual amongst natural satellites in just how large it is compared to the major planet that is orbiting. That this center of mass is noticeably not at the center of Earth. It's this offset quite a bit, and Earth is orbiting around this point. That's what this green orbit is showing. So yeah, that's that's what Feynman was talking about. Earth, just as the Moon is falling, towards this point, center of mass, and Earth is also falling towards this point. So that's the Earth-Moon orbital mechanics. And I can show you the kind of orbital mechanics of the solar system. So let me actually do this. I'm gonna go to Sun, so that the Sun is kind of centered. Okay, so this is kind of the view that's difficult to obtain in real life, because in order to have this view of the Sun and the planets orbiting around the counterclockwise, you have to be basically above what's called ecliptic plane. That's the plane of the solar system. We do have some spacecraft that has gone out of this plane of the solar system, and but it's like one of the Voyager spacecrafts have gone in that direction, but that journey takes a very long time and has to travel through quite a bit of void, because most of all of the major planets in the solar system is in this very thin plane. And this actually comes from physics. So these bright green lines, they are all orbits of major planets. So if I go in this view, you can kind of see it. So in the very outermost, this should be, guessing, I think it's a Neptune. Is it Neptune? Let me try to click it. Yeah, it's Neptune. So Neptune, Uranus, Saturn, it's just Saturn, and this is Jupiter. By the way, I'm starting with those outer planets to show the scale. This is how far away those outer planets are. And Jupiter, it's the distance is being. Oh wait, that's distance from me, not Sun. So that might not mean anything. So that's a Jupiter, and all the inner four planets, they're in this tiny circle here. So if I want you to actually see where they are, I really need to zoom in so that you can distinguish them. This is Mercury. Sorry, those asteroids are really in the way. That's a Mercury, the closest the planet. That's that was Earth. That's Venus, and this is Earth, and that's Mars. And when we talked about Kepler's laws, in the lecture I did talk a little bit about how Kepler, there was some element of fortune in that Kepler was analyzing motion of Mars, because when you look at orbit of planets like Venus, this is really close to circular orbit. So if Kepler was analyzing orbit of Venus, or analyzing orbit of Venus, he might have concluded, yes, planets do go around the sun in a perfect circle. And that wouldn't have led to the discovery that he did make. And I think Mercury does have a quite elliptical orbit, but Mercury is harder to observe from Earth because it's closer to the sun. So there's many parts of its orbit where it's simply not possible to observe it from the Earth unless you go outside the atmosphere so that you can just see it anytime. And so this is the orbit of Mars, and imagine it with the sun at the center. I think I'm more or less directly above it, so that if its orbit is perfectly circled, then this should look perfectly circular. Just notice how close to a circle it is. It is elliptical in that I think the center should be somewhere around here, but the sun is not at the center. It's at one of the two foci or focuses of the ellipse. And this is uh, how remarkable the level of precision in the data, in Tycho Brahe's data, that you need for Kepler to be able to figure out the orbit of the Mars doesn't exactly fit a circle, but it's quite close. So, and that's why that's the beginning of modern astronomy, one that's centered around collection of accurate, reliable data, instead of philosophizing about how the heavenly bodies should move and whatnot. No, so the reason we have this ecliptic plane, the plane where things, most big things are in, is because of conservation of angular momentum. If you think about life cycle of a solar system like ours, you can imagine kind of stellar nursery, a cloud that's eventually going to collapse. The vast majority of the mass will form this star, and the rest of the stuff will be hanging around as the planet. And when you have a collection of gas, I think it's not too unlikely to imagine that that collection of the gas might be rotating in some direction. It would be actual. It would take quite a bit of coincidence for that gas to be perfectly kind of not have a net angular momentum. It just it'll have some random value of angular momentum. And the thing about the gravitational interaction is that it's a central force. It's a force that acts along a straight line between the two objects, and with under influence of central force like gravity, angular momentum is conserved. So as the cloud of gas collapses and becomes the solar system, it has to conserve angular momentum. And what that means, if a mass that's farther away is moving in, it has, if it was orbiting very slowly, it has to now orbit, it has to move faster in order to conserve angular momentum. And as it moves faster and faster, at some point there's a kind of a balance between centrifugal force and the force of gravity pulling it in. So so if you imagine angular momentum pointing one way as that cross product vector quantity, in the plane that's perpendicular to that angular momentum, there will be some limit to how close the material can come in. At some point, their orbital speeds will be enough to keep them in a stable orbit like this. But in the direction perpendicular to that plane, that's where things can collapse all the way down, and that's where you see this plane. So the net angular momentum of the solar system is in the direction perpendicular to this plane. And that's also the reason why when you look at the solar system, there's a kind of natural direction that everything is rotating in. That's the direction that corresponds to the net angular momentum of the solar system. So you could imagine in the early stages, there might have been some pieces flying around. In fact, we still have some pieces flying around in the asteroid belt. There's quite a few asteroids here. I'm just trying to click to the biggest one, Eris. That's Ceres. That's the biggest asteroid. It's the only one in the belt big enough to be classified as dwarf planet. So there might be some, tiny pieces here and there that's going in the wrong direction. That's orbiting clockwise from this view rather than counterclockwise. But if you imagine solar system existing over geological timescale, billions of years, when there are objects just flying in, going the wrong way, at some point it's going to hit something else. And over those millions, billions of years, with the things colliding, everything will, the things that achieve kind of stable arrangement will be the things that are going in the roughly the same direction. Um, so yeah, in this view, so I can also speed up the time to show some of the things that we talked about. We talked about Kepler's law. So in the picture of the orbital path, you've seen illustration of, I guess, Kepler's first law, that the sun is at the center of the ellipse or elliptical orbit. I can demonstrate. Can I? Um, Kepler's second law doesn't like hit you like a brick as much as Kepler's third law. So I'm gonna speed this up quite a bit so that orbit of Mercury will be relatively fast. I think I need to speed it up a little bit more. So okay, at this time scale, about 1 second in the simulation is 1 day, 1 Earth day. So you can see how quickly Mercury is moving, not that fast. Let me speed it up a little bit more so that it looks like Mercury is whizzing by. Okay, so in this time scale where every second is about half a month, maybe, you can see how quickly Mercury is orbiting, how quickly Venus is orbiting, how quickly Earth is orbiting, how quickly Mars is orbiting, and how quickly Jupiter is orbiting. And I hope you can see that these inner planets are moving faster. It's not just that they completely orbit more quickly, it's that they are also moving faster. Their actual speed is faster. So these outer planets, they have a long orbital periods. Like even Jupiter, the innermost of the outer planets, take 11, 12 years to complete one orbit around the sun. And yeah, so that's a kind of the view. And so compared to Saturn and Uranus, the Jupiter now looks pretty fast compared to Saturn and Uranus, which are slower than Jupiter. And so yeah, that's Neptune, outermost major planet. And way back in, when was it, 2006, 2007, that's when this redefinition of planets happened. So before then, they didn't really distinguish between major planets and minor planets or dwarf planets. Things were just a planet or not a planet. So during that time, one of the objects that used to be classified as planet was Pluto. And I think I can identify Pluto if in this picture with the orbital orbits marked. I think I can identify just from the features because there are some things that are just odd, weird about Pluto. So I think it's easier to see if I go out of this plane. So look at the plane from the side view. So with the major planets, as I was saying, their orbits are in this tight range of ecliptic plane. One of the things that looks off about Pluto is that orbital Pluto is not in the ecliptic plane. It's at a bit of an extreme angle. And I think which one would it be? I want to guess that this is Pluto. Let me see. Yep, that is very center of Pluto, Charon. Charon is pretty big compared to Pluto. So it's the moon of Pluto. They are both double tidally locked. So look at the orbital Pluto, compare it to orbit of the major planet. That's kind of the first thing that, as people were learning more about the properties of Pluto, that as they made long enough observation to project its orbit, which actually takes quite a bit of time, 250 years, that it doesn't fit the same pattern that major planets have. And that's because it's kind of a different material, I guess. So these objects that you see with the orbits projected out, these are the confirmed dwarf planets I guess that they are called the trans-Neptunian object, TNO. Their orbits are mostly beyond the orbit of Neptune. So Makemake, is this Eris? I'm looking for there should be Eris. Oh, I see. Eris is this one. So Eris, who's discover, it's one of the first dwarf planets because it's the discovery of Eris that really put status of Pluto as planet kind of in danger because there are ways in which Eris is very similar to Pluto. So look at the mass of Eris. That's about 23% of the mass of Moon. And when you look at the mass of Pluto, I can select the Pluto. I'm just going to use the search feature. So many. So mass of the Pluto is actually less than mass of Eris, 18% of mass of Moon. So these two objects are similar in size. Um, and they kind of share similar-ish orbit. Eris is maybe a little bit farther out than Pluto is, and they are actually their orbits are so elliptical that there's portions of their orbit where Eris is actually inside the orbit of Pluto. But the point is that they are both of similar size, so it's kind of nonsensical for us to say, oh, Pluto is a planet because we found it earlier, and Eris is not a planet because we found it later. That's just so arbitrary, and we scientists try not to be arbitrary, although often we end up being arbitrary, but we try not to be. So there were the International Astronomical Union, they were trying to develop some kind of consistent definition. And one criteria that they settled on is the criterion of what's called clearing the neighborhood around its orbit. And really, that's the thing that you can, kind of a concrete thing you can look at between the major planets and these many trans-Neptunian objects that are kind of like a planet. They are bigger than asteroids, but we kind of want to avoid defining them as planets because there's just so many of them. It was nice when we had 9 planets with Pluto. You know, 9 is a nice number. But if we start making Pluto and Eris planet, and we would have to make these planets, then we would end up with 20 or so planets. And it's so unwieldy, like the label of planet wouldn't mean anything. So the distinction that they settled on was um, how the orbital features. So as you look at here, you can see with the orbits of the major planets that they are the dominant body within their orbit. There's no other body of a similar size that's occupying the same orbit, and that's kind of a factor of gravity. These major planets are large objects in their orbit. They influence all the other things around their orbit. So either things that are near them either get captured as a moon, or they get accreted into the planet itself, or they get knocked out of the orbit entirely. So so all these bright green orbits of the major planets, they show neighborhoods that's been cleaned out by the planet, the major planet. These minor planets, they are the kind of, they are big enough in their own orbits, but as you look at it, there's quite a bit of overlap between orbits of these different bodies of Pluto and Eris and all these other dwarf planets. So they haven't cleared their neighborhood. They are not big enough to push away or somehow gravitationally dominate other objects that are in a similar orbit. So, so based on the criteria, these trans-Neptunian objects, which are also outside of the ecliptic plane, they are not major planets. So let me show one of the comets. The most famous comet that you might have heard of is Halley's Comet. So that's this is another astronomical object whose discovery is prehistoric, as in even in the earliest written material, you can you can find references to a celestial object that with our better knowledge of astronomy, we can identify this, oh, that is Halley's Comet. So if Edmund Halley wasn't the person who discovered it, why is it named after him? It's named after him because he's the one who recognized the periodicity of Halley's Comet. That it's a celestial object that becomes visible in our sky once every 75 years. And, that's suspiciously similar to typical human lifetime. So this is the kind of comet that everyone sees maybe once in their lifetime. So appearance of Halley's Comet is associated with superstition like end of world because it's a kind of once in a century thing. Every time it appears, people alive then have never seen it before. It's sign of times, world is ending, and uh, Haley recognized this kind of sighting. It's occurring on some regularish interval, and I think Haley's he's around after Newton's synthesis of his theory of gravity and derivation of Kepler's laws based on the mechanics. Uh, he, I think, I don't know, I'm terrible storyteller. I'm terrible historian. I'm even worse a storyteller. But I imagine Haley looked at the records of sighting of the comet and recognize that there's a periodicity. So it becomes visible to us when it comes near the kind of near the sun in the inner part of the solar system. And when astronomers describe a very long period object, they forgetting the name of the process they go through. They can often, with that benefit of identification of the object, they can go back to the historical astronomical records that go back to the kind of the Middle Ages, the Islamic scholars, ancient Chinese records, and with the knowledge of what it is they're looking for, they can identify, oh, this record is referring to actually this Halley's Comet. And they do that with the Halley's Comet and with the other objects as well. So, like, Pluto, it has period of 450 years, and that kind of measurement can be made more precise by looking retroactively at previous records that didn't fully recognize what that object is. So let me do this. I think I can use Halley's Comet to illustrate Kepler's second law. So you can see with this orbit here, I'm trying to move it around so that you can get a better view of the three-dimensional arrangement of the Halley's Comet's orbit around the sun. So it is outside of the ecliptic plane. It's at this angle, and it's a hugely elliptical. So so the focuses of the ellipse that this elliptical orbit is at. So one of them is at the sun, Kepler's first law, and the other one is over here. So it's elliptical to a degree that none of the planets or dwarf planets are. So let's see what view is the. I think this is decent enough view to kind of see the orbit of Halley's Comet. I'm going to reset the time to our current time. So Halley's Comet last appeared in the 80s. So right now it's very far from the sun. It's like a halfway point between its two sightings. So so where it is now, you can't. We can calculate where it should be, but the core of the comet is so small that even with the most powerful telescope, we shouldn't be able to see. But that's where it should be based on its known orbital characteristics. So I'm gonna speed up the simulation time a little bit so that the motion of Halley's Comet in this outer edge is still visible, because it's gonna take it another 30 years or so to come near the sun. So let me speed up the simulation time. enough that it looks like it's moving. Um, okay, maybe that's enough. So I can see that a little dot that's moving there, and it's moving slowly. And as the simulation is fast enough that every second right now is about a year. And I want you to, and I'm just going to leave the simulation speed alone so that you can make a proper comparison. See how quickly or slowly Halley's comet is moving. So so Kepler second law says that the areas. Oh, sorry. Let me just pause it briefly. The area swept out by the line connecting the planetary planet. In this case, it's comet, but Kepler's second law applies to comets as well. The area swept by a line connecting this object to the sun, area swept by that line in some amount of time is equal for all the points in the orbit. So out here, that line was longer. So as it moves slowly, the kind of the pizza slice that it's sweeping is fairly sizable. Now, as it's moving in, the line gets shorter. So in order for that line to sweep the same area, the comet will have to move faster and faster. And I'm gonna resume the simulation and watch how it gets faster as it gets closer to the sun. So near the perihelion, it goes by super fast. So the entire orbit of Halley's comet again is 75 years. I'm gonna just reverse the time a little bit so that we can look at that close approach a little bit in more detail. Uh, okay, I'm just reversing the time a little. Okay, good. Gonna reverse it again and oh wait. I can't reverse the while it's paused. Okay, and I'm gonna just zoom in a little bit so that we can look at the perihelion of the Halley's comet with a little bit more. Okay, and I'm gonna slow it down so that it doesn't go by so quickly. Okay, um, so so as it's entering kind of the range of the asteroid belt where Ceres is, so So that is around, or that is going to be around 2061, beginning of that year. Okay, and I don't know if the comet would be visible at that distance. So what makes a comet visible is, let me zoom in with a telescope to see if it might be visible. I don't think it would be. So yeah, so the comet doesn't really become visible until it develops that. Oh wait, it is developing the tail. Okay. So I'm gonna zoom in a little bit more. So you can see that. So the comet's core is a really tiny ice, dirty ice ball. That's the description of comet. And when it's way out, far away from the sun, that tiny ice core, it's basically not visible. It's a yeah, it does it. Yeah, the diameter is 11 kilometers. It's like size of a city, super far away. Can't see it even with the most powerful telescope. The part of the comet that becomes visible to us is this tail. And let me track the comet so that the camera will just follow it as it gets near the sun and then moves away. So around the beginning of 2061, that's when, with a really powerful telescope, you might be able to begin to see the comet. And start the simulation again. Oh, yeah, maybe a little bit slower. Um, and okay, faster. Okay, I'm gonna zoom out a little bit because I can't tell where the comet is in its orbit. Uh, it is okay. Okay, it's still beyond the orbit of Mars. Let me just track it until when it's inside the orbit of Mars. So somewhere here. Okay. So at this point, the comet would be somewhere at a similar distance as how far away Mars is from us. And okay, that doesn't seem to have changed all that much. So I'll move the simulation along until it's inside the orbit of Earth. And I think by this point, the tail should be much more visible. Yeah. So the sunlight is heating up the ice ball, and it's evaporating of stuff from the comet. That stuff is getting pushed out by the solar pressure, radiation pressure from the light from the sun, and that's forming this tail. And the tail of the comet, it's not tracing the path of the comet. It points away from the sun, and it's beginning to develop the two tail. I think the more volatile material points more directly away from the sun. This is the heavier dust. And let's see here, I'm gonna zoom out. And I think by this point is where the comet would be visible to naked eye observer without any telescope. And it's also near Earth, so that helps too. And as it gets, so this is the perihelion at the closest point to the sun. That's where the tail would be the brightest and biggest, and that's the so the comet was in the view at the beginning of the year 2061, and around the end of May, June, that's when it's at perihelion, when it's the brightest. It's scaring the most number of people, at least before we knew what it was. And it's going to take another few months to move out of the range and become invisible again. So it's moving out of the range of the orbit of Mars around here. So the comet would have been visible in the night sky for maybe a few months. So so yeah, that's a kind of orbital mechanic illustration that I can show with this simulation. Yeah, am I okay? Yeah, and there are other things I can do, but I see that I'm over time, so I think I'm gonna end it here. There are, I guess, there's a lot of fun things in the. So this question is about geosynchronous orbit, and I'll have to warn you that I'm using the term a little bit sloppily. I think in the aerospace engineering circle, there's distinction between. I'm going to assume this is my situation. This is my setup. My Earth is here, and as we all know, Earth rotates, and we'll say that we have set up our coordinate system so that uh, the axis that Earth rotates around is directly up as drawn. I'm not worried about the tilt of the Earth for now. So Earth has an equator, and I'm going to imagine a satellite that has been put into space around the Earth so that over a whole day, um, the spot it's directly over on Earth is the same spot throughout the whole day. So when you think through it, the only kind of extension of the great circle through Earth where that can be done is above the equator. Because if you're above any other spot, then as you're trying to get out orbit, you will be changing latitudes over time. So let me imagine my satellite somewhere here. So over a course of a day, the satellite will be orbiting the Earth one full. I guess it should be one full turn, since so over one whole day, the satellite is directly over this spot on Earth, and over a whole day, this spot will be moving around the Earth one full turn, and the satellite will also be completing one full turn, so that it's directly over the point throughout. That's the setup of the geosynchronous orbit. And again, there's like somewhat nuanced version of the term that you can look it up. I think I've seen it once before and then forgot which is which. We'll just use the term geosynchronous. It's asking what is the altitude of the satellite. Okay, let's first work out the radius in the sense of the distance from the center of the Earth to the orbital height of orbital position of the satellite. Let me call that R orbit. And after we work out that answer, we'll have to modify it a little bit. Because when it says altitude, it's really asking for this distance from the surface of the Earth to the satellite. And so there's a difference of the Earth's radius, which might be significant, might not be. We'll have to work out the answer to see. So the hint says consider the centripetal force on the satellite and follow the standard strategy. Okay, let me just take this snapshot and draw a free body diagram. So I have the satellite there. There's always gravity. Now, I'm not going to draw it downward because gravity points towards the center of the Earth, which in that snapshot is to the right. So there's going to be that gravitational force. And you think through, what other force is there? And after some thinking through, the answer should be no other force is there. It's that's it. This is the one force that's on the satellite that's it's orbiting Earth. So okay, and the kind of the mistake to make sure to avoid is not to use our usual formula of mg. This is what's valid near surface of Earth. And I have a sense that this is nowhere near the surface of Earth. So we gotta use the full version of gravitational force that we introduced this week, which is that the universal law of gravitation says that the magnitude of gravitational force is proportional to the product of the masses, the mass of satellite times the mass of Earth, and it's inversely proportional to the distance squared, or orbit squared. And to make the equality work, we need this gravitational constant, whose value is can be looked up. Wolfram Alpha can do that for you. So this is our expression for force, and in using standard strategy, I'm skipping some of the steps because it's a simple setup with one force. Where we should end up is writing out this expression. The acceleration is equal to net force divided by mass. So, this is my net force, g times m big M over r orbit squared divided by small m. So those will cancel out. And because this is circular motion, we know what the acceleration is in terms of kinematical quantity. V squared over r orbit. It's the same r as this thing. And I have a sense that this is not the most convenient expression. So let me rewrite it using the expression relating the tangential speed with angular velocity. I can rewrite this as r orbit times angular velocity squared. And let's see. Yeah, I think that's enough. So let me just write out a cleaned up version here, equating the far left hand side with the far right hand side. So the cleaned up version says uh, r orbit omega squared is equal to g times big M, mass of Earth, divided by r orbit squared. So we had to combine these two terms, right? And omega, this is a number I can work out in terms of all the known quantities because what omega will be is it's 2 pi times frequency, and frequency is 1 over period. So 2 pi over the period, and this period for Earth's rotation is 1 day. So I think these are numbers I can plug in as we are working out the numerical value of the answer. So let's just get an algebraic expression for r orbit, and we can. I'll use Wolfram Alpha to plug in numbers. I see a couple constants whose numbers I don't really want to look up. Let's let Wolfram Alpha do it. So I'm gonna collect all the r orbit on the left hand side, collect everything else on the right hand side, and then because r orbit will be cubed, take a cube root. So r orbit will be equal to the cube root of g times m divided by omega squared. So let me plug the numbers into Wolfram alpha. R orbit, which will be gravitational constant times Earth mass divided by, and I have to write out omega 2 times pi divided by 1 day squared, all of that to 1/3 power for cube root. Yeah, let's check how Wolfram alpha understood my input. That looks good, I think. Okay, it had a bit of an issue. It didn't quite put the day on the correct side of the fraction. So extra parenthesis to make sure it puts the day on the correct side. Okay, there it is. So it says the radius of the orbit should be equal to um, so 42,240 kilometer. 42,240 kilometer. That sounds like a large value. And if you look up the Earth radius is less than that, much less than that. It's so in terms of kilometers, 6,371 kilometer. Now it's less, but it's significant enough that when they're asking for the altitude, we have to subtract this out. So let's say we're gonna take the answer we had before, and then we'll subtract out Earth radius. That'll give us what it should be. Uh, so uh, so the answer that they're looking for the altitude will be 35,860 kilometers. 35,860 kilometers. It's a pretty it's fairly hot. It's far enough. I think there are some communication networks that are built on geosynchronous satellites, and one of their limitations is latency because of the speed of light delay over this long distance. Just a engineering factor. Starlink uses low Earth orbit satellites precisely for that reason, but it needs more number of satellites to make sure that every spot on Earth is covered all the time. So can a geosynchronous satellite be placed over the North Pole, South Pole? I think the intended answer here is no. The way I was explaining how you can only place it over the equator. But I think in aerospace engineering, there's some word they use for uh, things that are like in this orbit, but over the poles. There are satellites on that trajectory, I think. I don't think they call it geosynchronous. I'm not sure what they call it. Low Earth orbit is orbit around the Earth just outside the atmosphere. What is the period of an object in a low Earth orbit? So this is an interesting question where we can actually go back and use an expression that we ruled out earlier. We can go back to this expression and use this for the gravitational force. Because the thing is, they didn't give us the distance of low Earth orbit. It can be anywhere between like 100, 150 kilometers to a few hundred kilometers. I think International Space Station is at 200 kilometers. I think maybe might be off by a factor of two. Look it up yourself. um, so within that distance, so if it's hundreds of kilometers, it's much less than our Earth radius of 6,000 kilometers. So this would be reasonably good approximation. So we can use this for gravitational force and work out what the period would be. So let me write a version of these equations that has substituted this thing for the gravitational force. So that's going to be the acceleration r Earth omega squared is equal to the right hand side force divided by m will be g. Okay, so I think I still need to know r Earth. And let me write out what omega squared is so that I can get an algebraic expression for period. So um, r Earth times omega. I wrote that out here. 2 pi over t squared is equal to g. Okay. Just trying to do the algebra in my head. I'm gonna have t squared to the right, everything else to the left. Flip them around for t squared is equal to 4 pi squared r Earth divided by g. Take the square root for the period itself. Okay, let's plug that into Wolfram alpha and see what we get. Uh, oh, I already have Earth radius here. So square root of 4 times pi squared times Earth radius divided by gravitational acceleration. I think it'll understand that. We'll see. Yeah, I think that's right. Earth equatorial already per yeah, yeah, okay. Yeah, so it gives us a few different units. I guess this is the most convenient to memorize. About 80 minutes. So something like an International Space Station. It'll so if we are somehow in the space place where overhead you will see it, it'll come around every 80 minutes. It's super fast because it's at a closer orbit. Oh, and it's a demonstration of Kepler's third law that you will be learning this week. Um, so yeah, it's um, so that's the low Earth orbit. So you have a period that's equal to about 84 minutes. These are kind of good number sense numbers to know. You know, geosynchronous orbit is kind of large. A low Earth orbit period is kind of short.